Before we start jumping into our discussions about probability, we need to define a few terms that we're going to use in our calculations. The first term is we refer to things as an experiment. When we talk about probabilities, we're just saying we're going to do an experiment, whether we can actually carry it out, whether we use some kind of simulator. And we talk about the outcomes. These are the possibilities. I'll give you a couple of examples. If I roll a dice, it has 6 sides, so it has 6 outcomes. If I flip a coin, it has 2 sides, so it has 2 different outcomes. If I draw a card out of a standard deck, there are 52 outcomes in that deck. So the experiment would be flipping the coin, rolling a die, or drawing a card, and the outcomes would be the possibilities. If we talk about all the possible outcomes, they will sometimes refer to that as the sample space, and the event is a sample of outcomes that we want. We want to get a heads when we flip the coin. That's our event. We want to get an even number when we roll that die. That would be our event. It's one of the outcomes in the sample space, and the experiment is us actually drawing the card, flipping the coin, or rolling the die. So let's look at a couple of examples here. If I talk about rolling a 6-sided die, so the experiment would be actually rolling the die. The outcomes that I could have are those 6 numbers, and that's the sample space. Everything's going to come out of that, and an event would be something like, what's the probability of getting a 4? What's the probability of getting a 2? If we talk about tossing a coin, if I toss one coin to one experiment, it has 2 outcomes, a heads and a tails. So I could get heads, I could get tails. That's the sample space, and the event would be what I want to happen, a heads or a tails. Now, if I would do this twice, now I have a little more to look at, because it could be a heads, then a tails. It could be a heads, then a heads. It could be a tails, then a heads, or it could be a tails and a tails. So if I'm tossing 2 coins, these are my possible outcomes. One's heads, one tails, both heads. The other one tails and heads, or both tails. So this is my sample space, and one of these events is the probability I would look at. If I go even farther and I talk about 3 coins, you can still list them out, or sometimes we will do a heads, heads, tails, heads, tails, heads, tails. So this is a tree diagram with each one of these having my choices, and there would be another half to it that has all the tails and the same idea, but you'll notice I get a heads, 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 a heads, heads, tails, heads, tails, heads, heads, tails, tails, and then I have the other half. Tails, heads, heads, etc., etc. There's 8 of them all together. These are all the possible outcomes, so that's my sample space. The experiment is the fact that I'm flipping 3 coins and I look at a specific event. Now that we have a grasp of that terminology, we get into the formal definition of probability. Probability, we use a capital P, E stands for event. So the probability of an event happening are the outcomes that I want, the favorable outcomes, compared to the total possible outcomes. Now, sometimes we'll write our probabilities as fractions, sometimes we'll write them as decimals, sometimes we'll write them as percents. They all mean the same thing, they all come from this calculation. But the one thing you'll notice is that they always land somewhere between 0 and 1. If I have a probability of 0, it's never going to happen. If I have a probability of 1, it's always going to happen. And most of our probabilities land somewhere on that spectrum between 0 and 1. So let's go back to that tossing 2 coins. I want to look at the probability of getting 2 heads in those tosses. So here's all my possibilities. This was my sample space. There are 4 outcomes. One of them is 2 heads. So what I want to happen, there's one way. What could happen, there are 4 ways. So my probability is 1 out of 4. Again, we can write this as a decimal. We can write it as a percent. They all mean the same thing. They all talk about tossing 2 coins and getting 2 heads. If I take that deck of cards, a standard deck has 52 cards, and I talk about the probability of drawing an ace. There are 52 total possible outcomes, but I'm only looking for an ace. There are 4 of those. 4 out of 52, if we reduce that, 1 out of 13, we can leave it as a fraction, change it to a decimal, whatever we want to use for our format. If we talk about drawing a heart, there are 13 hearts in a deck of 52, so that's what I want to happen. There are 52 cards altogether, which reduces to 1/4. Again, 0.25 or 25% or whatever makes sense to you. Sometimes you'll even see these probabilities written as a comparison. Now, one of the things we get into when we talk about probability in different events is this concept of mutually exclusive events. So when we have 2 events, we're naming them A and B, and they have no common outcomes, we take the intersection of A and B, they don't have anything in common, we call these mutually exclusive. So if I wanted to take the probability of the union of 2 events, here's the symbology for that. I take the probability of the first event and the probability of the second event, but I have to subtract off any repeats. Okay, I'll say that again. If I have 2 different events, I add those 2 and subtract off the repeats. Now, if my 2 events cannot happen at the same time, if they are mutually exclusive, then I don't have to subtract off those repeats. I just add the possibilities for those 2 events. And that's what we refer to as mutually exclusive. So let's look at a couple of examples and see if we can find out what this mutually exclusive is all about. So this says we're going to select 1 card from a deck of 52. So notice it's only 1 event, but I'm looking at 2 different possibilities. I want to know the probability that I'm going to draw a heart card or a face card. Now I'm thinking about this. There are 13 hearts out of 52. So the probability for hearts is pretty easy. If I start thinking about face cards, there's a king, a queen, and a jack, but that's for each suit. And there are 4 suits in a deck of cards, so there are 12 face cards out of 52. So I'm going to add these 2 possibilities because I'm successful. I have a positive outcome for all 25 of these. But there's a problem with some of my answers. Over here, I counted the king of hearts, the queen of hearts, and the jack of hearts because they are hearts. Over here, I counted the king of hearts, the queen of hearts, and the jack of hearts because they are face cards. So I counted things twice. Hearts and face cards are not mutually exclusive. So I can't just add 13 and 12. I'm going to have too many. I counted the king of hearts, queen of hearts, and jack of hearts twice. So I'm going to take this calculation and I'm going to subtract off those 3 repeats. Now when I add these, I have 13 out of 52 and 12 out of 52, which was 25. But I'm going to subtract off 3 of those, so I get 22 out of 52. Now I should reduce that. They're both even. So 11 out of 26, that's my probability of getting a heart or a face card. My second example is very similar. I said the probability of getting an ace or a black card. There are 4 aces, and there are 26 black cards. But there are also 2 black aces. So I have to take those ones that I counted twice and subtract them off. So 4 plus 26 is 30, minus 2, there's 28 successes in this case, positive outcomes, favorable outcomes. There are 52 cards that I'm drawing from. If you want to think of it in terms of a game, I would win 28 ways out of the 52 possibilities that I get out of that deck. So again, not mutually exclusive. Now let's look at this example. I've got this pie chart here, and it talks about the age of US workers. So I've got 16 to 24-year-olds, 25 to 34, 35 to 44, all the way around, and the percentage of the population that fit into those categories. So if I talk about the probability of 35 to 44-year-olds, it's already a percentage for me. So I'm looking for this percentage. 23%, so 23 out of every 100, or 23% is my probability. If I look from 35 to 54, I have these two. Here's 35 to 44, here's 45 to 54. I need to add those up. 23% plus another 23%. There is a 46% chance that I select somebody from those two groups. Notice I can't fall into both of these categories. I can't be this age and this age. So these two are mutually exclusive. They cannot happen at the same time. Unlike our black ace, where they could happen at the same time, and I had to subtract them out, these are now mutually exclusive. My last example, same thing. The probability of being under 35, so I don't want this one, I do want this age here, and this age here. So I add those two. They are also mutually exclusive. I can't be 21 years old and 30 years old and fit into two categories. I'm only one person. I only fit into one of these two categories, so they're definitely mutually exclusive. If I add my percentages, I get 37%, or 37 out of 100 as my probability. The next thing we have to talk about with probabilities is the difference between an independent event and a dependent event. An independent event is where two events, where the occurrence of one event has no effect on the occurrence of the other event. We're not talking about drawing a card and getting a red or an ace. That's only one event. We're only drawing one card. What we're talking about now are two different events. Notice that we have this A and B. We take the probability of A, the probability of B, and we multiply them. Now they may have nothing to do with each other. Think about the probability of rolling a 1 and drawing an ace. Those two things have nothing to do with each other. They're independent events. I can do the probability of rolling a 1. There's 1 on a die. There are 6 sides. That's my successes, what I want to happen, compared to the possible outcomes. For an ace, we talked about it earlier, there's 4 aces out of 52 cards. Because these events have no effect on one another, I do their probabilities individually, then I multiply them. Now, you get some small decimals. We get some strange looking fractions. I'm sure that reduces, but that decimal is my probability of rolling a 1 and drawing an ace. So if I would actually roll a die and draw a card out of a deck, I have a 4 out of 312 chance of actually getting a 1 and an ace. Now, I put this one up here because it uses the same deck of cards. It says the probability of drawing an ace and drawing a red card after replacing. This is the key. Because on this one there are 52 possibilities. As long as I put the card back, there's still 52 possibilities. There are 4 aces. That's how I'm successful here. That's my favorable outcomes. Over here, a red card, 26. That's my favorable outcomes. These are independent events. I multiply those. Now, the interesting thing about this, even if these weren't independent, if they were dependent, let's say I didn't replace that card. I still have a 4 out of 52 chance for getting the ace, But now my chances over here changed. I'm now only dealing with 51 cards, and I've got possibly one less ace here, so I get into some more complicated calculations, but ultimately we're still going to multiply because it's two separate events. Now we have to do a little more because we don't know what that first card was. My last example. They like to deal with marbles. They like to use examples that deal with marbles. So here are my marbles. I've got 4 red, 3 blue, 5 green. The first probability I want to do is just the probability of red. So think about favorable outcomes. There are 4 things that I want to happen, the 4 red ones. But there are more than that here. So my sample space has 4, 5, 6, 7, 8, 9, 10, 11, 12 marbles. So if I reduce that, I have a 1 in 3 chance, 33% of getting a red marble. Now, I said the probability of a red or green. I'm still drawing from the same sample space of 12 marbles, and I'm still only drawing 1 marble, but I have more ways of winning. I have 4 red, I have 5 green. If I add those up, I get 9 out of 12. I should probably reduce that or turn it into a decimal or a fraction. So this reduces to 3/4. I have a 75% chance of drawing a red or green marble. The last 2 I changed. Now I have 2 events. So now we're dealing with independent and dependent events. I'm going to replace them. So the probability of drawing a red marble and then drawing a green marble, and I'm going to put it back. Okay, so I'm going to do these as 2 separate events. We already talked about the red. There's 4 red out of 12. For the green, there's 5 out of 12. Since these have no effect on one another, they are 2 separate events, 2 separate draws. I multiply those 2 numbers. So I get 20 out of 144. And again, I can reduce that. I can turn it to a decimal. I can turn it to a percentage. If I didn't replace my first marble, it might read like this. What's the probability of drawing a red and then drawing a green without replacing? So now I have to think about my red marbles are still 4 out of 12, but my green marbles are only out of 11 because there is 1 less marble. I still have 5 ways of having a favorable outcome, but now my calculation changed a little bit. I still get the 20 on top, 20 favorable outcomes, but my bottom number has changed. I have to take 12 times 11. So it's going to actually increase my chances a little bit of red followed by green.